Your audio is on. Sunita, your audio is on.
আমি তো দিলুম, কিন্তু আমি যে কি করে হেয়া হব, ওরা আমাকে দেবে তো, অ্যালাউ করবে তো নাকি? আমি তো কি এটা, না আমার আর ভিডিও করি দেওয়াই আছে, শেয়ার স্ক্রিন।
Good afternoon, sir. Good afternoon, Vasudev Datta, sir. Can you hear me? Hello? Hello, Vasudev Datta, sir.
You know, to share, na?
Hello. Good afternoon, sir. Hello. Good afternoon, sir.
Hello.
Sir, we'll start the session at sharp 3 o'clock, sir.
Yeah, 3 o'clock. You have to allow me to share the screen.
Yes,
no?
sir.
Yeah.
I will, sir.
Okay, thank you. গরম রয়েছে আর বাড়াতে ঠান্ডা নাকি? আর 3 o'clock বলেছে।
Excuse me, sir. I just made you co-host, sir, so that you can share your screen, sir.
Okay.
Okay.
Now I share the screen. Hello. Can I share the screen now?
I can't see your screen, Vasudev.
Okay, I just will.
Yeah, now we can. Now we can.
It's okay, no?
You are about which portfolio? Very good. Oh, very good. Okay.
For every jury, the day before we practice the whole speech and everything.
Who with who?
Mohana. She is a designer, so she'll understand all of this. And like,
Okay.
so I didn't want to take help from my classmates because everyone is anxious. So I always take help from her. This time she gave 3 pages of criticism. She was like, you should mention this.
Inputs.
Yeah. Not criticism, inputs.
Huh.
So I was very confident after that.
Yay.
Please let me know when to start.
Good afternoon, everyone. I welcome you all for the third day of 1 week online international E-Symposium on modern mathematics. This especially I welcome Sir Vasudev Datta, Sir, and his daughter Datta Madam. Now I call upon Maheshwari to introduce them to the audience.
Thank you, ma'am. Good afternoon, everyone. I B. Maheshwari, faculty member of Mathematics and Statistics Department, Arbiter Women's College. Welcome you once again. Day 3 of 1 week international on modern mathematics and Statistics Department, Arbiter Women's College. I have the opportunity to introduce our speaker of the session, Vasudev Datta. Sir has completed MSc in Pure Mathematics at Calcutta University. Sir has completed PhD in Mathematics at Indian Statistical Institute, India. Sir has started his career as visiting fellow at TIFR Mumbai in 1998 to 1990. Sir has worked as a visiting mathematician at ICTP Trieste, Italy in 1990 and also at ISI Bangalore from 1990 to 1992. Sir has worked as assistant professor and associate professor at Indian Institute of Science from 1992 to 2005. Now, presently, Sir working as professor at Indian Institute of Science. Sir received gold medal from Calcutta University for first rank in MSc Mathematics in 1982. Sir also received Sir C.V. Raman Young Scientist Award of the Government of Karnataka in 2001. Sir has been awarded elected Fellow of Indian Academy in 2009 and also in 2014. Sir has published 48 research articles in Archival journals, 1 survey article in journals, 3 articles as chapters of book, 3 articles in journals of science education, and 1 extended abstract in conference report. Under Sir's guidance, 4 students has been completed their PhD and 9 students completed their master's and graduate projects. Sir's current research interest in combinatorial topology and PL topology, convex and discrete geometry. Welcome, sir. And Sir's daughter, Dr. Ipsita Datta, ma'am wants to share her experiences. So ma'am has completed her M Math at Indian Statistical Institute, Kolkata, with distinction. Ma'am has completed her PhD at Stanford University in USA. Presently, ma'am has been working in Princeton, and ma'am held Mariam Mirza Khani Fellowship at Stanford University. Ma'am's publications are Lagrangian composisms between enriched knot diagrams, a polyphore proof of Gromov's non-squeezing theorem, Ma'am presently a member of Institute for Advanced Study at Princeton, USA. Welcome, ma'am.
Sorry, you didn't tell anything about mom. So mom is not here. So she didn't know that she has to share. I gave it for 1 week back, but there is no response. I'm sorry. So I'll talk only. Ma'am has gone out. Ma'am was waiting even up to yesterday that she thought that she will share her experience, but nobody told that and nowhere it is mentioned. So I'm sorry that she has now gone out.
Okay, sir.
Uh,
Welcome, sir.
Yeah, I'm sorry, but she was even morning asking whether there is anything mentioned that I have to share my experience. Nowhere it is written. Or nobody shared, nobody told this thing as a reply of her CV that she will be doing. Okay, anyhow, I'll talk. Yeah, thanks for this. Thanks, and sorry, Uma, for this confusion. Okay, so can I start now? Shall I start now? Yeah.
Yes, sir. You can start.
Okay.
You can start.
Okay. Thank the organizer for giving me opportunity to talk in this E-Symposium and talk to this college and MSc student. And okay, and I saw there are lots of good speakers. I initially confused how much technical thing I should talk. So I have in between. I am trying to make more story and example for the BSc MSc student. And since it is a mathematics conference, international level, I'll give some results and definition, but technical things as much as possible I'm avoiding. I hope it is okay. Yeah. Okay. So these semi-regular maps, also called tilings, maps or tilings on surface means it's a surface, break it in pieces and each one is this. So I'll come to the definition, but before that, just let me come with this example. All of us know these 5 Platonic solids: the tetrahedron, cube, octahedron, dodecahedron, and icosahedron. Why this thing is related to my talk, I'll tell you. These are beautiful solids. Okay, and so this tetrahedron, cube, octahedron occur in nature as crystal. But the dodecahedron and icosahedron occur as skeleton of microscopic sea animal like this. There are sea animal, you can see this, that one is this icosahedron, its skeleton, and one is dodecahedron. And also there's intrusion that in the excavation of Montelova near Padua, Padua, they revealed that these dodecahedron things are known even 2,500 years ago. And these are in the in fact, the earliest Pythagoreans, even Plato's time also, these things are known, this Platonic solid. Why this is so special, I'll come to this. So now, if you project this boundary of this Platonic solid on the sphere, then on the sphere you get this a tetrahedron, you get that 4 triangle, this is the cube, and this is the octahedron, this is dodecahedron, this is icosahedron. If you project it, you will get a very uniform picture on the sphere. And so this is the story of hello, is there any confusion? Okay, now next, little less known about the Archimedean solid. There are 13 Archimedean solid, and they are very uniform, because if you look to the any vertex of any of them, they are same. This vertex also there are two hexagon and square. These also these. Moreover, that there is a symmetry which sends any vertex to any vertex, keeping this fixed. So what is called that vertex transitive action is there. So these Archimedean solid, there are 13 such beautiful solid, and I'll explain this thing. And so they have name and so on. Each one is very uniform. They are not as uniform as Platonic solid, but they are. I'll come to this. What is that? This. So the Archimedean solid take their name from Archimedes, who discussed this in a now lost work. Papias referred to it, stating that Archimedes listed 13 polyhedra. During the Renaissance, artists and mathematicians valued pure forms with high symmetry, and by around 1620, Kepler had completed the discovery of the 13 polyhedra, as well as defining the prism and antiprism. In geometry, Archimedean solid are the semi-regular convex polyhedra composed of regular polygons. Each face is a regular polygon meeting in identical vertices, excluding the 5 Platonic solid and excluding the prism and antiprism. What does it mean that identical vertices? Identical vertices mean that each pair of vertices are symmetric to each other. That is, a global isometry of the entire solid takes one vertex to the other, while the whole solid is remains same. Such a solid is now called a vertex transitive solid. We'll discuss this thing. So these Archimedean 13 are all are vertex transitive or solids with identical vertices. And other than this, there are two series of such solids. They also have the same property, that vertex transitive solid. One is the series of prism, prism with hexagon or octagon or any n-gon, and then prism, and then there is an antiprism. Antiprism is it's clear that antiprism means that both sides are n-gon, but little moved by 2 pi by n angle, and then joined by this. So I have given few picture. For example, if you do it 2 pentagon, it is this, or octagon has this color picture. So these are also vertex transitive solids. And I'll come to this, that why only these are things. So the result says, but before that I want to give some example. So torus is one object known to us. We also know various uniform tiling of the torus. Here are some considered few. We'll just discuss more. For example, in this one, through each vertex there are 6 triangles, and the second one, through each vertex there is 1 square and 2 8-gon. So that's picture, that means one this, and this is through each vertex there are 3 hexagon for 1.4 square. Then from one vertex there are 1 triangle and 2 12-gon, and through each vertex there is 1 square and 1 hexagon and 1 12-gon. I'll show some more. So there are 6, all are different type and very, very uniform. So it is not the Platonic solid. You can get other object also. So here is on the plane such thing. So the following 11 symmetrical tiling of the plane, Grumbaum calls such tiling Archimedean in parallel to the Archimedean solid. We'll discuss this later, why there are 11 types. And each type, it says that this number shows that, for example, 4, 6, 12 means to each point there is 1 4-gon, 1 6-gon, and 1 12-gon like this. Okay. Now, hyperbolic plane or hyperbolic disk. I'm not going to go to any abstract mathematics, but hyperbolic disk is the unit disk with some metric. It is hyperbolic, but moreover that what I'm talking here about the regular tiling. So in hyperbolic geometry, uniform hyperbolic tiling is an edge-to-edge filling of the hyperbolic plane or hyperbolic disk, which has regular polygon as faces and is vertex transiting. It follows that all the vertices are congruent and the tiling has a high degree of rotational translational symmetry. Some examples are given here. Some more example. So type I have given, so hyperbolic plane. And now there is on the solid, there is one more example. This is called pseudo-rhombic cubo-octahedron. So Gumbam observed that a 14 polyhedron, the pseudo-rhombic cubo-octahedron, meets a weaker definition, namely of an Archimedean solid, in which identical vertices means merely that the faces surrounding each vertex are the same type. It may not be some automorphism sense, but for example, this is the one of the Archimedean solid, but this one also has each point, to each point there are 3 square and 1 triangle, but one can show that it is not vertex transitive, little weaker condition it is satisfied. So Gumbam pointed out that a frequent error in which authors define Archimedean solid using this local definition, but omit the 14th polyhedron. If you use this local definition, then you have to consider this one also. If only 13 polyhedra are to be listed, then the definition must be global symmetry of the polyhedron rather than the local. So now let me, after this all the example, let me give some definition. Otherwise, it is difficult to explain the things, but very limited definition. So if I have a graph embedded on a surface, then when I take out the graph, then there are lots of components. Closure of each component is called a face. So for example, if graph, then it can be some triangle, some square, some pentagon, like this, a simple graph. Now, if all the faces are these two disks, and the intersection of any two intersecting faces is either a vertex or an edge of this graph, then G together with that all the faces is called a map or tiling of the surface. So tiling means, like all the example I'm giving, that all the vertices, edges, and all the faces, they give a tiling of the surface. The vertices and edges of this graph are called vertices and edges of this tiling. Now this is just one definition, don't bother much. If I have a vertex in an edge and this edge in a face, then such a triple is called a flag. Flag means take a face, take one edge, and take a vertex of that. So this why flag? Because this I need a definition for this. Okay, so example of few tiling and their types I define. So here is a tiling. There are 3 triangle and 1 square. So there are vertex to which there are 4 triangle. So that's what the notation, this vertex, there are 3 to the power 4. And there are point where there are 2 triangle and 1 square. So 3 square and 4. So this we denote by this notation is for this first one. Similarly, second one, there are vertex with 8 triangle, there are vertex with 6 triangle, and there are vertex with 4 triangles. So this, and in this one, there are each vertex there is 1 triangle and 4 square. And in this one, it's not, it is difficult to see, but through each point there are 7 tangles. Now, when we have such a tiling, then through each point that all the, say for example, this point, then there are 4 such faces. They some sense form a cycle. The square, triangle, square, square, square. This round of this. So such a cycle we call a phase cycle. Okay. And so the type we define in terms of this phase cycle. For example, this one we denote by 3, then 4, 4, 4. So 3, 4Q, or like this. So define vertices. So we define this. Changing the page. Yeah. Now, as usual, in any category, we like mathematics, when we say 2 groups are same, that means they are isomorphic. So in any category, we have to define what is called isomorphism. So here also I define isomorphism. So 2 tiling are called isomorphic if there is a map and its inverse, both are homomorphism. And homomorphism means it is a graph homomorphism which sends faces to faces. So that like any other subject that there is isomorphism. And automorphism means isomorphism from that tiling to itself. And this automorphism form a group, and this called automorphism group. And we call a tiling regular if the automorphism group acts transitively on the flags, set of flags. For example, all the 5 Platonic solids, they are regular. If you take all the flags, then automorphism group acts very strong group of symmetry. The maximum possible symmetry that any, not only vertex to vertex, any flag goes to flag under automorphism. And a tiling is called vertex transitive if the automorphism group act transitively on the vertexes. That means for take any 2 vertex, there exists a automorphism which sends that one vertex to another. And we call a little weaker thing called semi-regular or semi-equivalent if the type of each vertex is same. For example, just in the previous, this example, the third one, it is semi-regular because all the vertices are same type, but and 4th one also, but not the other one. So the semi-regular. So clearly a regular means vertex transitive and implies semi-regular. So the 5 Platonic solid, they are regular. And if you consider vertex transitive, they are 5 Platonic solid and 13 Archimedean solid. All these 18s are vertex transitive. And one extra 14th one, that is semi-regular but not the previous one. These all the implication of these. Okay. So semi-regular thing. So sometimes this extra condition, regular or vertex transitive, it is difficult to work with this because you don't know how to use it. So extra condition does not imply that you can classify easily. Sometimes much weaker condition, the semi-regular condition, we can classify the objects. And then we see out of that how many are regular, how many vertex transitive, and so on. And yeah, here I just wanted to say that some inequality, that there's some communal quantity. So if you have a regular p-gon, then angle is this one, p minus 2 pi by p. Therefore, if there are if there are ni pi gon at a point, then total angle at that point this. So this quantity, and if you take sum over all the vertices, this angle, no, this is, sorry, this is one vertex. Now this angle sum for a sphere, it is less than 2 pi. For plane or torus, it is 2 pi, and for hyperbolic plane, it is greater than this. That's what we say, that this combinatorial, very simple-minded, this quantity, it is deeply related to the geometric object, that how much curve, or whether positively curvature or curvature, zero curvature or negative curvature related with this combinatorial object. So, but we are here only bother about the combinatorial thing. So we consider this quantity, and we see that whether this angle sum is less than or equal to or greater than 2 pi. And this thing related to Euler characteristic and so on. Actually, for without assuming any geometry, one can check that if you have a closed surface, then this angle sum, this thing is related to the Euler characteristic of this thing. Okay. Sometimes the pages are not moving. Okay. Now I am considering the type of vertices I told. So these are the type of the vertices. First 18 are the type of the vertices of 13, 5 platonic solid and 13 Archimedean solid, and these are the for prism and antiprism. So this is the result, that if X is a boundary of a platonic solid or Archimedean solid or a prism or antiprism, then X is semi-regular tiling of S2, and that implies that the type of that vertex there is one of them, and therefore that this angle sum is less than 2. If you add pi both sides, then 2 pi angle sum. A converse of these three implications are also true. So namely, that X be a semi-regular tiling of type this on a 2 manifold. If it is less than 2, then this belongs to, this is in A, that one of these. And if it is, and conversely, if it is one of these, then there is no such tiling on the plane. Yes? Any question? And if you have a semi-regular tiling on or map on S2, then X is boundary of one of them. This is the theorem that so these 18 and the two series, they completely classify the combinatorial object, completely classify the geometric object up to isomorphism. Sometimes, yeah. Now classification of semi-regular tiling. So this is as a theorem I put, let X is semi-regular tiling of the type P1. This means through each point there are P1 N1 P1 gone, and then N2 P2 gone, like, and NK PK gone on a 2 manifold S. If S is simply connected and this sum is less than 2, then the surface has to be S2, and X is boundary of platonic solid, Archimedean solid, a prism, antiprism, or the pseudo rhombic by octahedron. Now for real projective plane, the same results is true. It is known that the quotient of 10 centrally symmetric vertex transitive tiling of the two sphere are all the gives all the vertex transitive tiling of RP2, like by quotienting you get it. And we have seen that these are all. So namely, if you have a semi-regular tiling of the projective plane, then its type is these 10 types, and they come from the as a quotient of corresponding tiling of the plane. And therefore, all are vertex transitive. Now, for next, I am considering 11 type of vertex type, and they are the vertex type of that 11 Archimedean tiling on the plane. I have shown the picture. So now let X be a semi-regular tiling of type P1 to the power N1 up to Pk to the power Nk. Then X is a Archimedean tiling of the plane, imply that the type is one of these type. And therefore that implies this angle sum is 2. And converse of this thing is true. We observe that if you have this condition, that if you just assume that this angle sum is 2, then that these are the only possibility. You can see that, and if you do little bit algebra or combinatorics, you see there are lots of other such people you get, but what we can prove that tiling is not possible with them. So you are assuming tiling, so only these 11 are possible with this. So that's what now this uniqueness of the Archimedean tiling. Archimedean tiling we saw 11. Here is the theorem that let X be a semi-regular map or tiling on the plane. If the type of X is in B, that about 11, then X is an Archimedean tiling. That means isomorphic to this. So there are only 11 types. And let X be a semi-regular tiling of the type this on a 2-manifold. If S is simply connected and this sum is 2, then S is R2 and X is the Archimedean tiling. In particular, X is vertex transitive. So Archimedean tiling of the plane also classified by this combinatorial identity, like this is 2. This quantity 2, this simple combinatorial equality gives the complete classification up to isomorphism of the Archimedean tiling of the plane. Because what I am trying to say that sometimes the geometric condition and or using group theory, automorphism, or even some number theory condition is very difficult to handle, but sometimes this simple combinatorial condition gives the complete classification. Now I'm talking about the semi-regular tiling of the torus. Let X be a semi-regular map or tiling on the torus of type this. Since Euler characteristic is 0, it follows that this sum is 2. Therefore, this type is one of the 11 types. And it is known that for each of the 11 types, there exists a vertex transitive tiling of that type on the torus. In particular, there are exactly 11 types of semi-regular maps on the torus. It is also known that for each type, there are infinitely tiling of the torus. We have seen 6 vertex transitive tiling of the torus. Now we present example of other 5 different type of tiling on the torus. So these are the example of others. But for each type, there are infinitely many. I'm giving one such example. So here is first one is say 3 cube 4 square. That means for each vertex there are 3 triangle and 2 square. So the next one is 3 to the power 4, 4 triangle and then a hexagon. You see. The next one is 3 4 6 4, and this one is 3 6 3 6, and similarly this one 3 3 4 3 4, like this type. all the known semi-regular tiling of the torus are quotient of Archimedean tiling. For some types, all the known semi-regular tiling are vertex density. And recently we proved the following, that all semi-regular tiling of the torus and Klein-Bottle are quotient of the Archimedean tiling. Only they come from Archimedean tiling quotient by discrete group. And if you let X be a semi-regular tiling of the torus, and if the types are like this 3 to the power 6 or 6, 3 or 4, 4 or this, then X is vertex transitive. So all of them are vertex transitive for all these 4 types. And for other 7 types, there exists semi-regular tiling which is on the torus which are not vertex transitive. There exists which is vertex transitive, there exists which is not vertex transitive. So there are 11 types of tiling, semi-regular tiling on the torus. 4 of them always vertex transitive. That means automorphism group act vertex transitively, and 7 of them possible vertex transitive or not vertex transitive, and examples of both are there. And for Klein-Bottle, the story is simple, that if you have Klein-Bottle semi-regular tiling, then the following possible 3, 4, 5, 6, 7, 8, 9, 10 types of things, not 11, one of them is missing. And each of the 10 types, there exists a semi-regular map on the Klein-Bottle which is not vertex transitive. So there are, you can't say vertex transitive. There are example vertex transitive or not. So here is one example where the this 4 type, this type, the Klein-Bottle. Now let B be vertex of a tiling. If the type of vertex is this, then this is said to be the combinatorial angle sum. The tiling of the hyperbolic is said to be hyperbolic if the faces are regular polygon on X, and one can prove that if the surface has genus greater than 1, then Euler characters is less than 0, and in that case this angle sum, it is greater than 2. So we must have hyperbolic tiling in this case picture. So we know very little about this hyperbolic tiling of the surfaces and plane. So here are some results. So if you have a closed surface with Euler characteristic less than 0, then the number of semi-regular tiling of S is finite and at most this quantity. So therefore only finitely many. This is the result. So here are some example, some more example, hyperbolic tiling. Now, say you can draw the tiling that may not be regular, very irregular way. But what it says that hyperbolic plane, whatever you do regular or irregular way, you can make it geometric. Because up to isomorphism, you can make a regular. That's what I say. It follows from the classification of semi-regular tiling of S2 the following: if T is a tiling of S2 with the vertex type K, then there exists a unique semi-regular tiling of S2 with regular polygon and vertex type K. So therefore, you can make lots of irregular one, but regular one you can make of the same vertex type unique one. Similar results are also follows from the classification of tiling of R2 that when angle sum is 0. And for a hyperbolic tiling, we prove the same thing. Namely, let tau be a semi-regular tiling of the hyperbolic plane with vertex type K. where alpha, that angle sum is greater than 2, then tau can be geometrized. That is, there is a semi-regular tiling of the hyperbolic plane by regular polygons with vertex type k that is isomorphic to T. Moreover, any two such tiling isomorphic to tau are related by a hyperbolic isometry that takes vertices and edges of one of these two other. So therefore, it is sufficient to consider the topological thing. So because any topological tiling you do of vertex type K, you can make that one as a geometric up to isomorphism. So there are infinitely many types of hyperbolic tiling of the plane. Now you know that why it is not possible to classify, and there are lots of questions also, lots of things not known. We just got some result, maybe we wrote one paper only. In fact, there exists semi-regular tiling of type PQ. That means there are Q p gone through each vertex on the plane whenever this quantity Q into P minus 2 by P greater than 2. And you can see there are infinitely many such quantity. And following two types results are known. So there exists hyperbolic tiling of type PQR if and only if one of the following is true. PQR greater than equal to 7 or P even and this quantity, or there exists a hyperbolic tiling of this type if and only if one of the following conditions are true. These things are known. There are lots of this type of when degree 3 vertices through this or 4 through this, it's known. One of them 3. If one of them is not 3, then we got some results of this, namely, the pages are not moving, sorry. Okay, it is better. Okay. So there are infinitely many types of tiling. Okay, we told this result. Now next one is recently we are able to construct several hyperbolic tiling of the plane under extra hypothesis. Namely, that we prove the following theorem that there exists hyperbolic tiling of type P1, P2, I mean, one P1 gone, one P2 gone up to one PD gone. I don't say they are distinct. If these following conditions satisfied, whenever there are say P1, P2 say same, say X, Y, and in another place Y, Z is there, then X, Y, Z also should appear in this. Or there are hyperbolic in this, if X, Y, and Y, Z appear, imply these appear, and if 3 is there, X, 3Y, I mean, among these things, say P1, P2, P3 is one of them is 3, and then P3, 3, P3, some P4, then it says, then this also should be there in that. Then such hyperbolic tiling is exist. Let K be a cycle type which satisfies the hypothesis of any of the above two theorem. Suppose two element of K uniquely determine the rest of the cycle triple. Then there exists unique semi-regular tiling whose vertex type is K. Moreover, in that case, the tiling is vertex transitive. Observe that if you consider this quantity, then two of them, if you choose, it is not uniquely determined. For example, if you say 4, 4, then that doesn't mean next one is 6 or 4. So it's not uniquely determined the things. But if all are same, then it's uniquely. So what it says that any two of them satisfy uniquely, then this. Okay. Is for example, if you have P, Q of anything, if you choose two of the P, then it uniquely says that you have to remaining Q minus 2 type of thing. So it is uniquely determined. So this theorem says then there exists one and it is unique. Now on technical lemma, that sometime I told that if you have sometime that equality satisfied, but still there is no tiling because of these obstructions. There is some restriction. This technical lemma. So now I say the problem you can ask that classify all the K tuple such that there exists a semi-regular hyperbolic tiling of type. So I believe that that there are two conditions. One is this is the necessary condition, and another necessary condition is this, that they don't satisfy the previous lemma, that those three conditions. These are the two necessary conditions, and I feel they are sufficient. So one can construct, but I don't know. Similarly, you can ask the classify all the P1 to the power n or Pk to the power nk such that there exists a vertex transitive hyperbolic time. And what I believe is, see, we saw that there are this type where more than one semi-regular tiling is there, but out of that only up to now all the example what I saw, that one of them is vertex transitive. So I believe that if there exist among all these things unique one which is vertex transitive. And then I asked that similar question for each closed surface of negative Euler characteristic, but even I don't have any conjecture for this, even I don't know. Okay. So here I give you reference of that what I am working 3 years, and here are some reference for other people who are related to this. And I think I'm stopping 10 minutes before. And if there are question you ask, so lots of picture I have taken from different websites. So I thank the appropriate website, and this presentation is not for circulation. Since I have, you can take it, but don't circulate it, because lots of them, the plagiarism I'll face or in face. Okay, thank you. So there are 10 minutes, so I like to answer the questions. I have finished it, so 10 minutes before. So if there are any question, I would be happy to answer.
Professor Bashidev?
Yes.
I'm Rao here.
Okay.
Yeah, I have a question.
Yeah, please.
I've read some article in which they said the football which people use in matches, soccer ball,
yes,
is not actually a sphere.
Yes.
It is a kind of regular solid of the type you are describing.
Yeah.
In the sense, it is a tessellated surface, and it has a particular structure and so on. Can you please tell us more about the design of the football that people use?
Yeah, football. So it is actually one most stable one is pentagon and hexagon, and the one of the model. Maybe I go to one of the platonic solid. The corresponding things is used nowadays. There it is not all. They are not regular. Let me go to the beginning.
Okay.
Okay, next I'll show you that one of them is used. Yes. This is the one truncated icosahedron. Initially, this was the most stable one. the left side down.
Okay, right.
This was known as very stable one.
Okay.
But nowadays it is not used that by they are regular or gone. So they are T-shape and so on. I don't know the different type of stability they consider. But the old days first consider this one.
Okay.
Truncated icosahedron.
Okay. So there is an agreement among all the clubs and people how to tessellate?
Not this thing. I think what is called FIFA decide, I think.
Decided on a surface. And it is not in your list. Okay.
It is FIFA. Also, you know that surface also changes, something glossy and right weight, what exactly weight. So there people do and so on. But one thing, since Euler characteristic is 2, you can see if you can put any number hexagon and 12 pentagon you can do.
Okay.
12 pentagon and 0 to any number of hexagon you can do, you can maintain the Euler characteristic 2.
Okay.
And this one is the most stable because to each point, you see, because you have to have this the minimum configuration with hexagon and pentagon.
Okay.
You can calculate because through each pentagon you should have the hexagon, through hexagon, pentagon, and since one is odd and one is even, the number should be like this.
Okay.
Yeah. This is Archimedes. Okay, thanks. So you know that you play soccer also.
Thank you. Yes, thank you so much. One more question of a simple sort. Have you used computer programs in your actual classification work?
No, I have not used. Actually, for Euler characteristic positive or 0, it is completely understood. And hyperbolic, you know what are the condition possible, but the main thing is whether triangulation is possible or not. And one of the postdoc was there with me, Arun Maiti. He was trying to construct using this thing. And also I have not directly used, but I had a student MS project he was doing. And so I asked him to classify some of them with hyperbolic plane with degree 4, then degree 5, because degree 6 onwards we have result, but degree 3, 4 also known, then 5 case. So 5 case, what are the combinatorially he proved that what are the possible, some 30 cases and so on. But whether for each one it is possible or not, I think 2 or 3 he still couldn't do, and he was trying to construct using computer.
Oh, wonderful.
Yeah.
Yes.
So I don't know what is the final status, because then that postdoc and MS student, I told them to complete it and write an article, but I don't see, because if they write, at least they will show me. Yeah. So computer, not much, but little bit the students are using.
Using. Okay. Thank you so much. Yeah. Thank you.
Hello.
Yes.
It's Uma speaking. Please share your lecture notes with us so we can. We won't circulate. It's only for our understanding better.
You already saved it? No, not that.
No. Okay. Actually, lecture notes.
No, lecture notes.
The slides, I mean.
This full slide. Okay,
I'll send you. Slides.
I'll send you by mail. I'll send you by mail.
Yeah, please. Okay. Thank you.
Yeah.
Thank you, sir, for your lecture on semi-regular maps on surfaces. It's very interesting, sir. Now I call upon Maheshwari to propose formal vote of thanks.
I did.
Thank you, Shweta ma'am. It is my pleasure to present vote of thanks on behalf of Department of Mathematics and Statistics, RBVRR Women's College. At the outset, I thank our today's resource person, Basudev Datta sir, for accepting our invitation and delivering a wonderful lecture on semi-regular maps on surfaces. Vertex transitive tilings of the torus, uniform or vertex transitive tilings of the hyperbolic plane, semi-regular tilings of the two spheres, and uniqueness of Archimedean tilings, hyperbolic semi-regular tilings of the plane. It's very interesting, sir. We are thankful for our Honorable Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mutyam Reddy, sir, and our Secretary cum Correspondent, RBVRR Women's College, Professor G. Sudarshan Reddy, sir, for their continuous encouragement in organizing program. I would like to thank our Principal Ma'am, J. Archita Devi, for her support. A special thanks to Shweta Srivastav Ma'am for organizing one week international E-Symposium on modern mathematics. Our heartfelt thanks to all the participants. Thank you, ma'am.
I'll stop sharing now. So it is time for Riddhi to take charge.
Will you stop sharing? Stop sharing, sir. Thank you, sir.
Yeah.
Thank you very much, sir. Thank you, sir.
Hello,
For readily accepting our invitation in spite of your busy schedule. Now I welcome Riddhi Shah, madam.
Hello.
Can you hear me, madam?
Yeah, I should just take my headphones because otherwise the voice may disperse. So let me just put my headphone on and then.
Now I call upon Harita to introduce Professor Riddhi Shah, madam.
Good afternoon, ma'am. Am I audible?
Yes, sure, you are.
Yeah. Thank you, ma'am. Good afternoon to one and all. Welcome you all once again to International E-Symposium organized by Department of Mathematics and Statistics, RBVRR Women's College. It gives me an immense pleasure to introduce the resource person of this session, Professor Riddhi Shah, for this one-week International E-Symposium on modern mathematics. Madam is a professor in School of Physical Sciences, Jawaharlal Nehru Technological University, Delhi. Madam completed her PhD in mathematics from Tata Institute of Fundamental Research, Mumbai, Masters in Pure Mathematics from Indian Institute of Technology, Mumbai, and Madam completed her bachelor's in mathematics from St. Xavier's College, Gujarat University. Her areas of specialization include dynamics of group actions, probabilities on groups, structure of groups. Madam has a vast experience in teaching of almost 30 plus years. She worked as a research associate, School of Mathematics, TIFR Mumbai, Fellow School of Mathematics, TIFR Mumbai, Reader School of Mathematics, TIFR Mumbai, and she worked as an associate professor at School of Mathematics, TIFR Mumbai. Presently, she is working as a professor of mathematics in School of Physical Sciences, Jawaharlal Nehru Technological University, Delhi. To her credit, she has received many awards. To name few: Indian Science Academy Young Scientist Award during the year for the year 1995. She awarded 2 gold medals for securing the first rank in bachelor's in mathematics at Gujarat University. Madam received a fellowship for senior scientist awarded by Japan Society for Promotion of Science. And she also awarded Alexander von Humboldt Fellowship during the year 1997 and 1998. Madam has published in many international and national journals, and many of them are part of best peer-reviewed journals. Madam, it is a great pleasure, honor for us to be here, madam. We are waiting for your lecture. I request madam to take over.
Thank you, Ms. Harita, for
you,
introduction. Just a slight correction. My university is called Jawaharlal Nehru University.
Yeah.
And am I allowed to share screen?
Yes, ma'am.
Okay. Let me find. Okay.
Madam, I have made you a co-host. You can share the screen. Yeah, we can see your screen, madam.
Okay, so wait, let me start. Yeah. So is that okay? You can all see?
Yeah, we can see your screen, madam.
Okay. So thank you very much for this invitation. It's a pleasure to talk in May 12 initiative, which is in honor of Mariam Mirza Khani. And I have given a very general title, Dynamics, but of course I will talk about some specific topics in that. And so what is dynamics? Dynamics is study of behavior of anything that moves or changes with time, whether it's oscillating pendulum or water waves, even violent ones like tsunami, or whether you study weather patterns or chemical reactions, the growth in chemical reaction or pattern in chemical reaction, or if you study growth in living organisms like growth of a cell or growth of living organisms like amoeba, bacteria, or even other species, animals, humans. You can also study neuronal activities in brain, or you can also study day-to-day changes in the price of shares and stocks. It could be in discrete time or in continuous time, right? You can study like what happens from today to tomorrow to day after, or you can study in a continuous time t. Could be regular or chaotic. Let's see some examples. So some more examples. So for example, population growth in a specific region over time or spread of disease infection in a given population. For example, last 2 years, people have been studying how COVID is spreading in a specific region or community. You can also study motion of a particle in a given medium. And I will just discuss two specific examples now. So one is called Belousov-Sabosinski reaction, which describes changes in chemical concentrations. For example, you can take C3 plus C4 plus couple as catalyst and use citric acid as reactant. And this can be modeled by reaction in diffusion type equation as given below. And these are the patterns you can see when concentration changes in this reaction. The other example is about mathematical models for neuronal activity. So how neuron in human brain behaves. So goal is to model how the voltage across the cell membrane changes over time. And Hodgkin and Huxley derived equations in 1950s to describe this. They found that neurons behave almost like electrical circuits. For example, I've given one example, trace from a bursting neuron related to breathing. So this is the activity which you then model, like how neuron behaves. So these are the models for that. It expands and contracts, right? So it's like pulse is going. It's like when your heart beats, what happens? So, okay, so these are examples. In mathematics, what is a dynamical system? So dynamical system is a space and a map on it. So, but we put a structure, right, on to study anything. So say X is a topological space and T is a continuous map on X. For any topological space, you can take, as an example, you can take subsets of usual space Rn, and you have the metric space on it, and you can metric gives topology, and you all know what a continuous map on a metric space is, right, or on a topological space. So your space X could be compact, like in Rn it could be close bounded, or non-compact, unbounded, like whole of R, for example. And T could be regular or ergodic. And here T could represent discrete or continuous time. Okay. So ergodic just means that, when you start with a point and you keep applying T, it would go everywhere. In a metric space, that is enough to say that for one X, that happens, 1 point it happens. So from 1 point, you can go everywhere. That is equivalent in a compact metric space to say it's ergodic. So for a map T on X, we define, for example, orbit of X. Means what? Orbit of X is, say, X, Tx, Tx, T square X, T cube X, and so on. That's called the orbit of X. You just take a point and you move, say, in discrete time somewhere, then you move again, then you move again. So you keep applying T to T again and again. That's called T orbit of X. And if T is invertible, then you can take whole orbit, which is T and X, N belongs to Z, where Z is set of integers. So you take X, Tx, T square X, and so on. And you take also T inverse X, T to the power minus 2X, and so on. So that's called T orbit of a point X. So you're given a space and a map on it. So its map is T from X to X. And you start with a point, and then you just keep applying T and see where it goes. That's called those set of points are called the orbit of X. T orbit of X. Example, you can take X any metric space and T a continuous map, say a unit disk in R2 with the usual metric, and T from D to D is a rotation map by fixed angle. Okay. So for example, you can take Txy is you're rotating a point in this disk by an angle theta along the angle from the origin. So that is, say, Txy is e to the power I theta xy. So this is the unique disk of radius 1. So all the elements inside and on the boundary are there. And this is cos theta sine theta multiplied by xy, which is actually cos theta x minus sine theta y, comma sine theta x minus cos theta y. This is a complex multiplication. And the translation T same as applying 2 by 2 rotation matrix to xy, which is cos theta minus sine theta, cos theta. That's your 2 by 2 matrix. Okay, that you are applying to 2 by 1 metric xy, and this is what you get. Namely, you take any point and you rotate it by angle theta. See here, in this angle theta, you can see. So you just take a point on the disk and rotate it. So disk is invariant under rotation, right? In fact, it's an invertible map because you can rotate forward or backward by angle theta, that will give you your T and T inverse. Well, not exactly forward and backward, but it's called clockwise. Clockwise and anti-clockwise, right? Rotation. So, okay. So is it okay so far? So these are my examples. Now we go to a specific kind of maps, which are called distal maps. Oops, what happened? Why is this thing on top?
Okay, madam.
It's okay?
Okay, madam.
Yes. So rotation of a disk is what we discussed. Now I'm going to talk about specific kind of maps, which are called distal maps. So what are distal maps? Distal maps are, so you have a map which is a homeomorphism from X to S, okay? And remember I talked about orbits. So the map is said to be distal if two distinct orbits stay away from each other. Means if I take points X and Y which are not equal, then in a metric space, there is a minimum distance between T and X and T and Y for all N. And of course, if I have this continuous time Tt, then Ttx and Tty remain at minimum positive distance for all T, in case X is a compact metric space. Otherwise, it means that if I take T and X and T and Y, they don't converge to same point in X, comma. So, for example, in X cross X, the orbit stays away from the diagonal. T and X, comma, T and X, T and Y, as N belongs to Z, stays away from diagonal. That's called distal. Distal actually comes from distance. So, these orbits don't, as you go along the orbit, it doesn't go close to each other. So this is a picture of David Hilbert, a famous mathematician, and the distal maps were introduced by David Hilbert. And they were studied by many mathematicians. You may have heard famous problems of David Hilbert's, right? Or you can go and look it up. So this was early, so this was early 20th century then when he had introduced around 1910 or so. So let's take some examples. For example, we took that rotation on the disk, that would all turn out distal because it's an isometry. Means if I take 2 points X and Y and I apply T on it, Tx, Ty are have same distance as X and Y. Okay. So if they are on the same unit circle, otherwise also, yes, it is an isometry. On the real line R, if we take a map, Tx equal to Rx, then it is distal if and only if R is 1 or minus 1. So what are you doing? Suppose your R is half, then you're taking Tx is half X, T square X is 1/4 X, and T to the power Nx is 1 by 2 to the power Nx, which converges to 0, right? And that is true for any X, right? If I take X, any X, T to the power Nx, when R is half, will go to zeros. But if R is plus or minus 1, then T and X is X or minus X for all X in R. So this preserves the distance, right? Because it will be XY or minus X minus Y. So the distance doesn't change. So whenever some map preserves distance, it will always be distal, because when you take higher and higher power of T, still the distance between the orbit points do not change. So as I mentioned, a half, if you take mod R less than 1, then T contracts the distance between any pair of points, because dx, dtx, ty will be R RTX, mod RTX TY, and mod R is less than 1, so that will be less than DTX TY. So the orbit of any point goes to 0. And this is true for any point. And the orbit of 0 is also 0. So you are not able to keep orbits away from each other in this case. And if mod R is greater than 1, then you can take T inverse and study that, because T inverse X would be R inverse X. Note that these are the invertible linear maps on R. So Tnx goes to 0, is R to the power nx goes to 0 as n tends to infinity. And T cannot be distal as T to the power n 0 is also 0 for all n. So orbit of 0 and orbit of any x, they both converge to 0, 0. So let's give a pictorial rotation, description of rotation on unit circle S1. So remember, we had a disk and we were rotating. The boundary was the unit circle S1, and you have a rotation again by e to the power I theta. So what do they look like? So they are isometries because you're rotating by fixed angle. So the order, the distance between X and Y and Tx and Ty are same. So if T preserves the distance, it's called isometry. Okay. So here is the periodic orbit on S1, which is 90-degree angle. So let's start with this one point, and you are going clockwise 90-degree. So again, see, I come back to same point, right? Now I start with what is called irrational rotation. So 90 is pi by 4, right? It's a rational multiple of pi. Here, the rotation is an irrational multiple of pi. Means your angle is R pi, where R is irrational. Okay, so you can see what happens. So this is one cycle. Now you go over second cycle, third cycle, and fourth cycle. If you do this infinitely many times, it fills up this space. The orbit becomes dense. What does dense mean? That it goes close to any points on the circle. It never goes. So if you start with a point X and take X, Tx, T square X, T cube X, and so on, it never comes back to X, but it goes close to X, and it goes close to any point Y in the unit circle. While in periodic orbit, like this 90-degree rotation, for any point, the orbit is just the 4 points, right? So if you take any rational multiple of pi, the orbit will be finite for any x. So both these are isometry and both of them are distal. So recall, as I mentioned, that T orbit on X is the these points X, T, and X, and so on, and N belongs to N. Or when T is invertible, it's T to the power NX, N belongs to Z, right? So if the map T is ergodic, as I said, on a compact metric space, ergodic just means so then it has at least one dense orbit and it's equivalent. Why? Because, so what is dense orbit? You take the orbit and take all its limit points. As a set, it has a limit, and that's called orbit closure. But so take orbit and its limit points, they should be whole of the space X. So set B is dense in X if the closure B is the whole set X, closure of B. And so X is the union of the set B and the set of all its limit points. So in case of irrational rotation on the circle, as I showed you by picture only, just as an example, but you can show mathematically that if it's an irrational the rotation by an angle which is an irrational multiple of pi, then you will get that orbit of any point in the circle is dense in the circle. So let's take another example. So this is an example of torus S1 cross S1. So what is S1 cross S1? It looks like surface of a donut. Consider the map TRS equal to RSS, where R, S belongs to S1. Okay. So what you are doing, you have a space S1 cross S1, right? Which is a subset of R3. I'll show you in a minute. It's a surface of a donut. The first coordinate you're multiplying by the second coordinate, and the second coordinate you're keeping as it is. So what happens here is that if your S is an irrational multiple of pi, then you are going to get that the orbit is dense in S1 cross S, because see, if I take t to the power ns, it's going to just, the second coordinate remains same. And the first coordinate changes, but within S1, it's some rotation by an angle of this R and angle of this S, and that is, if it is rational or irrational, it is finite or dense in this S1 cross S. So no orbit is dense in the torus S1 cross S1. This is of course not ergodic. This is an example of a digital maps, and in particular digital maps were introduced by David Hilbert, as I mentioned before, to study non-ergodic maps. Okay, so ergodic, the orbits go everywhere and so on, but here they don't go everywhere, and you want to study them, how it happens. So let's see some pictures to visualize this map on the double torus. So what, as I said, double torus is a surface of a donut. You can see a circle going in and out, right? And another circle going around. So it's S1 cross S1, right? And what does this map do? If I cut it somewhere, so it becomes a cylinder, wherever I cut that circle remains invariant. Okay, any circle, if I cut and it becomes cylinder, that becomes invariant. But if I apply T, what happens is, if I take this circle around, the big circle around, that will go like, it will, what I meant by twist, it goes around and comes back and joins again, like that. Okay. So nothing happens to the other circle, but this one goes like that. So this is just a heuristic description. So this is another view, which is, don't think of it as these lines. You know, torus is smooth, right? It's like surface of a donut or a cycle tire. And so it's smooth, but these lines are to show what happens when I apply T. Okay. So it goes round and goes in and comes back, right? And this is after a few, maybe 8 iterations. So again, it doesn't look like this. These lines are just to show you what happens if I took a circle and applied T, say 8 times. So it goes in, out, 8 times, and it becomes like that. Because that circle keeps shifting, right, every time. So, and if I go full this thing, it has done once. So okay, so this was a general example, but S1 unit circle is a group. You can do complex multiplication of points, and it is a group operation. It has inverse, and identity is the 0.10, right? e to the power I0 is the identity. So that's 1, 0. And real line R is also a group with addition, right? Or if you take Rn, n-dimensional Euclidean space, you have addition there and it's a group, right? So a group is said to be topological group if it has a topology which is Hausdorff and the group operations are continuous. So let's say Rn with the usual metric and x comma y going to x plus y is continuous and x going to minus x is continuous. And S1 with the complex multiplication with the metric inherited from R2 and S1 cross S1 with the metric inherited from R3. And GLNR is general linear group where you have matrix multiplication and inverse is also there, right? They are groups. Special linear groups are the n by n matrices with determinant 1. And they are all topological groups. What does it mean? GLNR, you can put a topology as a subset of Rn square, right? Because they are n by n, so n square entries in R. So, and this matrix multiplication is basically entry-wise, it is a polynomial equation. So they are all continuous maps, taking matrix multiplication and inverse in GLN. And if every group you can define homomorphism, right? Because what is homomorphism? Homomorphism is one which respects group operation, right? Txy is Txty, and so T is a map from G to G, and Txy is Txty, and Tx inverse is going to be Tx whole inverse, right? That's homomorphism. But if it's also homeomorphism, means it's continuous and its inverse is continuous, then it's called an automorphism of G. For example, on Rn, if you take any linear map which is invertible, T belongs to GLNR, since it's invertible, it's a homeomorphism and homomorphism both. You can see homomorphism is easy to check because it's a linear map. So, and we took this other map RS on the torus, that's also an automorphism. So remember, automorphism is a group homomorphism and it's homeomorphism. So you don't have to worry about other general abstract things. Just remember that what happens in linear Rn or S1 or S1 cross S1, or you have unitary group, which is a compact matrix group of matrices, right? So it's a group of isometries of Rn. And automorphism T of G to G is distal if and only if no orbit goes close to the identity of the group, unless the element itself is identity. So if X is identity, then Tx is identity because T is a group homomorphism, right? So identity goes to identity. But if X is not identity, when I take orbit X, Tx, T square X, and so on, or T inverse X, T to power, it should not go close to identity. Identity should not be in the limit of this sequence. So we study dynamics of automorphisms of locally compact groups when the topology in the group is locally compact. Don't worry about what this is, but you can, the GLNR, SLNR, Rn are locally compact. Okay. So one thing about, as it is using orbits to define maps, we would like to study behavior of orbits. So what happens? So a homeomorphism of T T of x, which is a topological space, is said to have minimal orbit closure, which is written as MOC, if the orbit closure of some point x are minimum of every point x are minimal closed T invariant set. See, this is the orbit is T invariant, so its closure is T invariant. But are there proper subsets which are also T invariant? Once I take closure, I have got one set, right? Closure of T and X, and I want to know whether there are proper subsets which are T invariant. So, okay, I was just wondering how much, yeah, half an hour I have, right? So, so this is the definition. MOC stands for minimal orbit closure. Now, if a homeomorphism T has MOC, then X splits into distinct T invariant components, which are these orbit closure. They don't intersect because otherwise they would become proper T invariant subsets. So, and then each orbit, so and T acts on each component, and we say that is ergodic. It just means that the orbit is dense in each component, right? So distality and orbit. So it seems, so if G is a locally compact group, don't worry about locally compact, I said, because actually the point has a neighborhood whose closure is compact. Every point has a neighborhood which is closure. So MOC implies distality, okay? Because you see, identity has its own orbit, right? Standalone orbit, because T is E, T square is E, T to the power n is E for every n in Z. So, and other orbits don't go close to identity because it, otherwise identity would become a proper subset, which is T invariant in those orbits. So MOC implies distality, but conversely, we would like to discuss the following question. Does distality imply this property, minimal orbit closure? So it's true that if T is distal, then orbit closure T n x n belongs to Z or TTX is a minimal closed invariant set. And this was already known for compact spaces like this rotation map and the map on the torus described above. I mean, compact groups. And so, wait, sorry. So it is indeed true that distality and MOC are equal for automorphisms of such groups G, and this was shown in 2012. It appeared in Journal of Free Theory. So contraction groups are another subgroups or depending on T, which is defined as this. Contraction group of T is defined as X belongs to G, T and X converges to identity as n tends to infinity. So if G is Rn, then contraction group is the largest subspace on which the eigenvalues of T have absolute value less than 1. So take all the generalized eigenspaces where the eigenvalues of T for Rn, T is a linear, invertible linear map, right? So you have eigenvalues and you take those. There is a subspace on which T has eigenvalue absolute value less than 1. And if the eigenvalues are equal to or greater than 1, then that is a different subspace. But where eigenvalue is greater than 1, then T inverse has absolute value greater than. Now, if you see that if my whole of Rn is this Ct, then every Tnx goes to identity, right? Or if Ct is non-trivial subset, then it would go to identity. So this is actually a subgroup, and in Rn it's a subspace, so it cannot be distal. So if T is distal, then the contraction group has to be identity for T and T inverse both, right? And what about the converse? Can we characterize the distality of T in terms of triviality of contraction groups? Yes, it is indeed true. This was a deep result, which is joint work with C.R.E. Raja from ISI Bangalore. T is distal if and only if the contraction groups are of T and T inverse are trivial. So this part maybe I will skip. The study of these distal groups and distal maps came from, was motivated by something about behavior of study of probability measures on groups. And on distal groups, they behave in a certain way, and there is a characterization done in terms of what are called pointwise distal groups, where the conjugation maps are distal. And for the measure, on the other hand, it is a probability measure on it, which behaves in a certain way. And then later it was also studied whether you can go study what happens to T on the group, and if you go modulo closed normal in T invariant subgroup, then you have a action of T on the quotient space, quotient group, what happens to that? So these pointwise distal have certain useful properties. Distal groups have so powers of probability measure, which are convolution powers, they behave in a certain way. So I will not go into that because that needs a lot of definitions. But that was the main motivation to start studying distal and pointwise distal groups. And then, but distal maps were studied for a long time. As I said, they were introduced in early 20th century, so by David Hilbert, so they've been studied for a long time. So let me go over to something else, because I want to relate this to work by Mariam Mirzakhani. So everybody must have seen a billiard table in physically or on internet, right? You must have seen players playing, right? So excuse me. So this is one example. This is a big one, and you have a small one here where, so there's a cue and you hit this white ball to make it go into these holes, right? Sometimes it can go straight, or sometimes you will hit against the wall to make it go to some ball at an angle, right? You hit at angle. For example, you want to hit this black ball from the side above, then you hit in such a way that it hits this left side wall, and then it goes into this middle hole. Most of you must have played carom in your childhood, and there also we have a striker, right? So sometimes you can't hit a coin straight into the hole, then you hit it on the side, and then at such an angle that it goes into a hole, right? Because you have a restriction of one side to use for your striker, right? So same way, mathematical billiard is a dynamical system in which a particle alternates between motion of a straight line and a specular reflection from the boundary. When the particle hits the boundary, it reflects from it without loss of speed. And as I said, it is a specular reflection. So you see, if it hits at an angle, same angle, it just reflects and goes. So this is called mathematical billiard, and this is stadium billiard shown below. Stadium means because the shape is like a stadium, right? Like a full football stadium or many other stadiums, right? So, well, they are not oval, but here it's not all are oval. So there is a related problem called illumination problem, like billiards. Okay, so what is it? So instead of particle, you have a light of ray of light, and suppose your boundary is a mirror boundary, then obviously the light will hit the boundary and reflect, right? And it will keep reflecting wherever it goes. So imagine a room with mirror walls. Okay, so all your walls are made of mirrors, and if you place a candle at some location in the room, will it illuminate every other point in the room? So as the light ray hits the wall, it reflects back at the same angle as the angle of incidence, like you saw in the stadium billiard, right? The answer is yes, if it's a square room or a rectangular room, because see, light travels in every direction, right? From a point source. Then because these are convex, rectangular or square, they are convex, or even that stadium billiard is convex, right? Because any 2 point can be joined by a straight line, the light will reach everywhere. It doesn't even have to reflect from the wall, right? It will reach everywhere. But if it is a funny shaped room, it may not happen. So what if the room has another shape, not convex? Convex shape, of course, any point to any point you can go. You don't need mirror wall also. So, excuse me, I'll just put this off. But I could have a room which is not convex and irregular. So here is a strange room with reflecting walls. This was made by Penrose. So you see it is not convex, right? There is this part on left and right which are not there, right? And so this is example by Roger Penrose in 1958. It says no matter where you put a candle, there will be some patch of positive area which will not be illuminated. So this is a surface in R2, so you can talk about area, right? And when you're saying, you're not saying a candle. So this is a room with mirror walls. You're putting a source of light at one point. So it's a point source and it is traveling. It's a bit like that particle traveling and hitting the wall and coming out. So no matter where you put candle, there will be some patch of positive area which will not be illuminated. So there, I think Nikita Agarwal talked about these examples. These are called 26-sided and 24-sided polygonal room with mirror walls designed by Castro and Tokarski and Castro, where if I put a source of light exactly at this one point in each of them, say left side, and then it won't reach the right side. And conversely, this point on the right, it will not go in. It will not illuminate this point on the left, but everything else will be illuminated. Now, these are Euclidean geometry examples. And now I would like to relate this to the work by, as you know, you must have seen, this is a famous quotation by this lady, which says, the more I spent time on mathematics, the more excited I got, right? You all have seen this picture before. Who is she? Anybody?
Mariam Mirza.
Right, yes. So you've seen these pictures, and this is a brief bio. She was a brilliant mathematician from Iran. She won a gold medal in the International Mathematical Olympiad twice, and second time with perfect score 42 on 42. Her research work was mainly about understanding geometry and dynamics, okay, but on hyperbolic surfaces. So we'll see what they are, okay. So it's not Euclidean metric, it's hyperbolic metric. She proved several path-breaking results in her PhD thesis, okay. And in the last few years, she, along with Alex Eskin, proved a famously known theorem, which was called magic wand theorem, which led to resolution of various unsolved mathematical problems. Why it was called magic wand theorem? Because of its applications. It's a very deep theorem, and there were so many conjectures, very difficult problems to solve, which were unsolved. And this theorem, just it's like waving a magic wand and getting what you want. So that's why it's called magic wand theorem. It's resolved all these unsolved problems, very deep unsolved problems. So what is a hyperbolic surface? Hyperbolic surface is the surface with hyperbolic metric. One example of hyperbolic surface is the surface of double torus. So we had one torus which was on surface of a donut. Here is a double torus which are joined together at one point or at one circle, doesn't matter. So this is a boundary, okay, it's not solid. And it's obtained by identifying opposite sides of an octagon, which I think Nikita also showed. Opposite means they're not exactly opposite, but they're equal side. For example, here top you can see A, and side you can see A. Those are identified. B and B are identified. D and D are identified, and C and C are identified. But they are not next to each other. None of them are next to each other, right? So all of them skip one side and then they are identified. So see, when you have a square and you identify opposite side, you get a cylinder, right? Then that cylinder, you identify top and bottom, you get a torus, which was that donut, surface of a donut. So that was like in a square, you are just identifying opposite sides, okay? Here you are identifying in a different octagon has 8 sides, 8 equal sides. So you are identifying not opposite sides, but skipping one side. So you get these double torus, okay? I think she showed you that earlier. So I don't have a picture how identification gives you. But now what is called illumination in translation surface, a double torus is an example of a translation surface, which is a finite union of polygons with choice of identifying parallel side of equal length, okay? So you can take any polygon, n polygon, and then those sides which have equal length, you identify one with the side, say side 1 with side 3, side 2 with side 4, 5, like that. So you're identifying those and you get this. These are called translation surfaces. So using the work of Mirzakhani, these 3 mathematicians, Leliv, Montel, and Weiss, proved that any translation surface M, there are only finitely many points in M which are not illuminated by a given point M in M. So if you put a light source at one point, it will go everywhere except finitely many points in the base. Okay. So, but here, instead of straight line, one has to consider light rays traveling along geodesics, the shortest path between 2 points on the surface. Okay. So when it is a hyperbolic metric and you're going Obviously, it's not straight line. You can also even otherwise see that on these surfaces, it's not straight line. So, but in Rn, it is straight line, right? The shortest distance. So you have a metric and you have the shortest path depending on that metric. And your light ray is traveling on that. So this is a picture of 2014 field medalist, which is Akhtar Avila, Martin Herer. Here is Mariam Mirza Khani with her daughter Anahita and Manjul Bhargava, who is of Indian origin. And unfortunately, in 2017, she passed away due to cancer just at a young age of 40. And she was already suffering from cancer for 4-5 years at that time. And when she got the medal also, she was suffering from it. And it was a great, big loss to mathematics community and especially women in mathematics. So this was my way of giving a little tribute to her. And with my last few slides are about activities of Indian women and mathematics. So this is one collage of different activities of what we call IWM, Indian Women in Mathematics. What is that? So this is a website you can see. So Indian Women in Mathematics is a collective of Indian mathematicians that has been in existence since 2009. The mission is to encourage more women to pursue higher education in mathematics, organizing events and networking opportunities that enable them to take up career in mathematics. So whether it's teaching or research, it's a career in mathematics. So this is the website, and you can see all our past activity and future upcoming. For example, so we have, let me show you a map here. So we have had all these activities. This is a map of India, and you can see that it's spread out. So one is what is called annual conference, and this year it will be in ISER Pune, sometime in winter. It's open to masters and PhD students and postdocs and faculty, teachers, researcher, anybody. Yes. Okay, and it's open to women as well as it's open to men also. It's not. Excuse me. Women are encouraged to attend, but it is open to all. Okay, and the other thing is regional workshop. So in fact, one annual conference happened in University of Hyderabad a few years ago. You might all know, in 2017, right? No, 16. I forget.
Biological groups.
So
To be there.
There was Hyderabad, IIC Bangalore, SNU, and then University of Mumbai. Yeah, so 16 it was. And then what is called regional workshop, which happened over a weekend, 1.5 day in different region of India. And then there is a visitors program where we invite distinguished women mathematicians from India and abroad to go to three places. 2 of them must be in a smaller regional, small town or non-metro places. And they give popular talk to encourage women in mathematics. And now last 3 years, we have these what is called winter school in mathematics, which is typically for second year undergraduate women students. to go to a place and learn, like it's a workshop, what is called school. So it is more, if it is offline, then it's 1 week. But in recent time, it has been online, conducted in the evening over 2 weeks. So that's for undergraduate people. Rest of the activities are open for masters and PhD and postdoc and faculty and anybody that is. But they should be enrolled in a master's program or above. Okay. So that is about Indian women in mathematics. You can look up. This year, the winter school is going to be in ISER, Tirupati. And there are also mini courses which are coming up, which are going to be, of course, online. So they are not put here. There will be 3 mini courses and anybody can attend. They are by very good mathematicians. Last year, we had one by Professor B.V. Limaye. And this year there are 3, and typically for all these annual conference and all, annual conference has all speakers giving talks which are women, and in visitors program 50% at least are women. Same for, no, visitors program all are women, but regional workshop 50% are women. So we try to put active women, and there are panel discussions, there are interactions where people can ask questions about things. For example, on 3rd of June, there is a May 12 talk by IWM, which is by a famous mathematician called Barbara Cafill. And she's from Ohio State University and very well-known mathematician. I will forward this to Miss Uma or to your department.
Yeah, thank you, madam.
You can distribute.
Please forward. Yeah.
It's open to everybody to attend, undergraduate.
Yeah, I know.
Okay, it's a 1 hour talk and some half an hour interaction. So, and it will be online.
Yeah, you have my email ID, madam.
Right. I will forward. And with
Please
that,
forward.
thank you.
And also forward your talk slides.
I can, but
lecture.
as Vasudev said, it is not for circulation. You can.
Yeah, not for circulation. It's only for our for our college.
Yes, okay. And all the figures and things are used from open sources in World Wide Web or from online. Okay.
Yeah.
I just wanted to mention, which Nikita may have also mentioned, there was an article on Mariam Mirza Khani called The Master of Artist of Curved Surfaces by Nikita, Geeta, Venkatraman and me. And many of the things from the last part about translation service, so on, is taken from there. And then there was also, Resonance is a popular science journal. So in March, they have a special woman issue, and you will see in this issue in 2019, you will see that there are very interesting articles by women mathematicians also in applied maths, on prime number theory, prime numbers, and so on. You might want to. So those are meant for undergraduate students. Of course, any of us can read, but undergraduates can understand. So it's very popular, and you might want to read those articles. Okay, thank you very much. And with that, I stop here. Sorry, I don't have a watch. I hope I didn't go over time. No, it's just 5. Okay. I thank you. Shall I stop sharing, or does anybody have a question?
Thank you. In spite of your busy schedule, madam, you have accepted the invitation.
Oh, it's a pleasure. Thank you very much.
Thank you, madam. for enlightening us on this dynamics topic. And in spite of your busy schedule, you have accepted our invitation, madam. Thank you very much. And now I call upon Harita to propose formal vote of thanks.
Thank you, ma'am. I deem it a great honor to propose vote of thanks on behalf of Department of Mathematics and Statistics for this technical session of International E-Symposium organized by Department of Mathematics and Statistics. At the outset, I thank our resource person, Professor Riddhi Shaman, Professor Jawaharlal Nehru University, Delhi, for making excellent presentation on topic dynamics. And madam, you made this session very interesting by explaining the concepts of dynamical systems on topological groups and distal maps, orbits of distant maps, contraction groups, illumination problems, using interesting examples, man. Once again, I thank you, man, for accepting our invitation. And also I extend my gratitude to Honorary Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mucham Reddy, sir, Secretary cum Correspondent, RBVRR Women's College, Professor G. Sudarshan Reddy, sir, our beloved Principal, Dr. J. Achita Devi, ma'am, Vice Principal, Dr. Kavita, ma'am, for their constant support in organizing this event. I would like to extend my heartfelt thanks to Shweta Srivastava, ma'am, Head Department of Mathematics and Statistics, for taking initiative in conducting of the event. And also I would like to thank all the members of the department for their cooperation. And my heartfelt thanks to all the participants for active participation. Thank you, ma'am, for giving me this opportunity.
Thank you. I want to mention one thing. So mathematics programs, MSc and PhDs in Jawaharlal Nehru University is under School of Physical Sciences, which has physics, chemistry, and mathematics, both MSc, PhD in all three different subjects, MSc Maths, MSc Physics, MSc Chemistry, and PhD in each of them. So, and it is the people applied through a national exam, and I believe this year it may be CUET, and any of the aspiring participants want to do an MSc in mathematics, they can look up our website of mathematics at School of Physical Sciences, JNU, and you can see MSc in mathematics and see how if you feel like applying and for it and giving entrance exam.
Thank you, madam. Thank you, participants. And we'll join for the next session on tomorrow at 3 p.m. by Professor Amber Habib, sir, on the topic. All of you, bye-bye.
Okay, so I stop sharing. Thank you. Bye.
Madam?
Yeah.
You can stop sharing the screen.
Yes, I stopped sharing the screen, and I will
complete, and it's
yeah. Okay, bye.
Bye. Thank you so much. It's been a pleasure.
Thank you. Bye.
We'll encourage our students to apply to JNU.
Yeah, also to IWM activity space.
Okay.